today we're just going to look at a linear momentum example, and it's going to be a two-part. One which will look at just a linear momentum problem where you have a force applied and you have to balance things out. The second one is going to be a more traditional impact problem that depends only on knowing what the initial and final velocities of the bodies are before and after an impact. So we're going to look at this collision, its focus again, linear momentum, and just maybe a little bit of a divergence in terms of the material to look at Newton's third law. And finally, again, returning to this idea of impact, but again, impact where you know what's happened at the beginning and what's happened at the end. So you're asked here to solve for or look at a problem where you have two masses, M1, M2, which are made up by welding together a block of gold. Gold, mass 1, a block of copper, mass 2. And you're asked to show how mass is important to Newton's three laws and what this means. And this is a problem that comes from can Newton's third law be derived from the second? Physics Teacher Volume 55, 2017, pages 236 to 237. In terms of starting this out, what I will typically do is I'll define my coordinate system, and this is a one-dimensional motion, so I'll only define x. And if I do that, I can immediately do the force balance. The force balance is a vector problem in the sense that force is a vector, and m1, m2 are masses, and the resultant acceleration, which I expect would be probably, in all likelihood, 100%, moving to the right, is a. So I can write that as force x and ax. But if I look at the individual components, I can take that gold element and say, okay, look, that's mass 1. And if I do that, then I have force F, which is the force that's moving to the right. And I have force 1 with respect to 2. And I can say force plus force 1 with respect to 2, m1a. And you'll notice here I've dropped all of the references to either x or vectors because I know this is a one-dimensional problem. The other component is mass 2, and that's force 2 on 1. And so in this case, the only component that I'm looking at, the only element, is the copper. And so I end up force 2 on 1 is equal to mass 2a. Now I can take that and then I can add in these two components. And if I add in these two components, then what I get is, over here, Newton's third law. And so that's kind of interesting in the sense that I can look at each of the individual components, and we've done problems like this where we've looked at breaking up everything and removing masses, but including their force or their contribution to the other mass. But the outcome of this is that I have the same equation as I started with on the previous slide. Then I have mass 1 m2, mass 1 v1 plus m2 v2 equals mass 1 2 v1 2. So this is the case of momentum, and if I assume plastic collision with v1 equal v2 equal v1 2, I end up with everything exactly the same as before, which is not a really outlandish sort of assumption here. The thing to remember is that v1, v2, and the final velocity of an element that is made up of welding copper and gold together will have the same velocity. So it's an additive property. So that's kind of a fundamental problem, and it's sort of not that terribly interesting other than just sort of defining what we're looking at. But let's take a look at another problem. This is a problem where we have two cars that approach an intersection. I have car A, which is starting out at 42 degrees and north of east. So north of east means just north and to the east. Over here, I have car B, which is traveling south. The two cars collide and move at 12 degrees north of east. One car was moving at the speed limit, 60 kilometers an hour. What's the other car speeding at? And so you have mass A here, which is given as 1,800 kilograms, mass B, which is given as 1,400 kilograms. So this is a problem where you're not given anything in terms of what happened during impact, so you assume that the impact has occurred instantaneously. And if you start out, because this is a linear momentum problem, it becomes a vector problem. And it's a vector problem in the sense that I have to look at velocity x, velocity y. And so I have only velocity a to start with, which is acting in the x direction, MAVA cos 42 degrees. So that's there. And then afterwards, I have both masses moving together, and they're acting at an angle of 12 degrees. So I have that here. At the other side, for the y direction, I have positive y, or positive y for velocity of a, sine 42 degrees. And I know that the velocity b, the block, is moving to the south. So that's negative. So I have mass a plus mass b times v sine 12 degrees. So I have two equations. I don't know one of the velocities. I know the other velocity, or I don't know what the other velocity is. So you have at the very top of this sine 42 degrees over cos 42 degrees minus mbvb mava cos 42 degrees. So that's the terms that were on the left-hand side, is equal to sine 12 over cos 12. So now I have a relationship between the two. And out of this, I'm going to get velocity b over velocity of a, tan 42 minus tan 12, ma cos 42 degrees over mb. So I have velocity b over velocity of a right there. And I get a relationship. And it tells me immediately that velocity of a was moving faster than velocity b. So car A is moving more quickly in terms of pre-impact motion. And out of that, I can tell you that it was going about 50% faster than it should relative to the speed limit, which was 60 kilometers an hour. So it ends up with 91.3 kilometers an hour. As usual, these are problems that relate to force, velocity, and time. It's really important that when you deal with any of these momentum problems, you have time somehow implicit in this. And time is not necessarily obvious. So, for example, in the last example, what happened was you had an instantaneous collision, which was time is equal to essentially zero. These are linear momentum problems, no rotation, and I'll probably end up doing an angular momentum slide later. And then mass is kind of a funny property. You kind of got to think about it a little bit, but what's interesting is tying sort of Newton's first, second, and third law together. And really they're kind of all together in there, and just realize that that's what's going on.